In this section, we are going to be talking about derivatives, chapter 3. We are going to start with the definition of the derivatives, and we will see the shortcuts afterwards. Section 3.1 is about the definition of the derivative and related applications, such as tangent lines, derivative at a point. Let's see. As you would see in here, we have a graph, and you will see that the blue one is the graph, and we have the secant line going through P and Q, as we have seen in chapter 2, and we have the red line, which is the slope that passes through P. The question here is to find the tangent line equation to the curve, which is y is equal to f of x, at the point P. Okay? The slope of the tangent line at P is the limit of this quotient, f of x0 plus h minus f of x0 over h. You remember this is the rate of change formula, right? We use this for the average rate. Okay? And we just take the limit as h goes to 0 and we get the slope from it. And I talked to you about that before. Okay? So here's the definition. We write it in a much more formal way. Slope of the curve y is equal to f of x at the point P, x0 f of x0 is this number, limit of this quotient. But we want to make sure that the limit exists. If the limit exists, means that the limit has finite value. Okay, well-defined value. The tangent line to the curve P is the line that's going through this point P and this slope that we find. Okay, so we can solve an example. In this case, 1 over x. 1 over x is going to have a slope which is negative 1 over a squared. This is a butterfly example, if you remember. This graph looks like a butterfly, if you remember that. And the slope at a is negative 1 over a squared, whereas the slope at negative 1 is negative 1. Okay? Because if you plug in negative 1 to this formula, negative 1 squared is 1, negative in the front, so it is negative 1, you get it, okay? And you see that in butterfly example, the slopes are negative because you see the tangent lines has, right, the tangent lines are decreasing, right? Do you see that? This is the tangent line and it's a decreasing line, so the slope has to be negative. This is a decreasing line here too. I'm not talking about the decreasing function, okay? Of course, this is a decreasing function and this is a decreasing function on the intervals that are defined, okay? And whenever a function has a decreasing graph, the slope is negative as well. You know that. Let me do this for you, okay? Okay, we want to slope of the function butterfly graph at x is equal to a. A is arbitrary point. We just write the formula for the limit, for the slope, limit of this quotient. We first calculate the quotient. Here we equate the denominators. As you will see, we are going to have some cancellations. I'm going to show the cancellations by using the red color. Okay. We rewrite it as follows: negative h over a times a plus h times 1 over h, and h we can cancel. Here we cancel this h with this h, and let's see what we have left. Next, we are going to take the limit of this. So I'm going to circle this with green. You see that, right? We are going to take the limit of this guy. Let's go back to page 2. In page 2 we have negative 1 over a times a plus h. In page 3 m represents the slope of the tangent line. We can directly plug in h0 because it doesn't make any undefinedness here. So the answer is negative 1 over a squared. So this is the slope at any point A. Let's find the slope at negative 1. We are done because we just found the slope at negative 1. We can write the tangent line equation at negative 1 as well. We are going to do that next. We are interested in the tangent line equation at a is equal to negative 1, and our function is 1 over x, the butterfly graph. Whenever x is equal to negative 1, the y value is negative 1 as well. So slope is negative 1, the points are negative 1, negative 1, and we get this equation, and you can leave it like that, no problem. Okay. You don't, excuse me, you don't have to simplify it. If you look at this graph, you will see the tangent lines at the point 2 and negative 2. The formula is negative 1 over a squared. You just plug in 2 and you get the slope negative 1 over 4. And similarly here, negative 1 over 4 for the slope at negative 2. Okay? See, these two tangent lines are parallel to each other, and their slopes are the same. Okay, so we are going to give a new definition, which is after seeing what the slope is in terms of the limit and the quotient. Okay, so we want to give this a name. We call this because we want to generalize this notion. We just don't want to focus on the slope and the line. We want to generalize this definition, just this thing, and we are going to give it a name, and the name is the derivative of a function of f at the point x0, and the notation is f prime 0 x0. F prime x0 is equal to limit as h goes to 0, f of x0 plus h minus f of x0 over h. Of course, again, as long as this limit exists, then the derivative of a function at a point x0 is going to exist. Okay, so actually this, let me make this a little bit bigger. This limit of this quotient is important. It means several things, and let's look at all the interpretations of this limit of this ratio, okay, of this quotient. It would mean for us that the slope of the graph of y is equal to f of x at the point x is equal to x0. We have just seen it. We have just seen that this is the slope. And it's going to be the slope of the tangent line to the curve y is equal to f of x at x is equal to x0. 1 and 2 are the same actually. It's the slope of the graph and slope of the tangent line. They all, okay, even if we write it differently, we mean the same thing here. Okay? And because you can find the slope of a graph by looking at the tangent to this graph at that point. Okay? So 1 and 2 are, they are the same. And the third one, the rate of change of f of x with respect to x at the point x is equal to 0, x0. Yes, this is the rate of change. If you remember average rate, if you take the limit h goes to 0, you get the rate of change of f. You just see the change of f around x0. So what's happening around x0, okay? We just get that information from this by looking at this limit. And then, okay, and this slope actually 1 and 2 is going to also tell us how this function is behaving. If the slope is negative, the function is going to be going down. If the slope is positive, the function is going up, which means increasing. So all these things actually, the derivative is giving us information about the behavior of the function f. Okay, and the last one, this would mean for us the derivative f prime x0, okay, at x0. Yeah, this is the fourth one, is the general name to all these applications, okay? So whenever we talk about the derivative of a function at a point, we would say that, oh, maybe in the applications they are going to be referring to the slope of the tangent line or slope of the graph or rate of change of the function they would mean, okay? So these are all we have here. Okay, next we want to just extend this derivative notion more. Like we want to see this derivative as a function. You will see how, okay? So let's look at the right hand side here. Right hand side is the limit of that quotient, you already know. On the left hand side, what's different here is we would use a here, right, instead of x. But if you change a to x, that would tell us that x could be any number. So when you have x varying, x changing, when x is a variable, so this f prime at that point x becomes a function, right? Because function means, as you change x, the value of the function changes, right? So instead of writing x, we just convert this derivative notion to a derivative function, okay? So that's a very good observation. Okay, so if you look at this blue graph, this is the original graph of f, and then we can talk about, so these are the derivative of f at x. So we want to see what is this. This is actually, this is a graph of seeing f of x plus h minus f of x over h. Okay. Pictorially, that's what you would see. Alright. And here z is x plus h, by the way. This distance is f of x plus h minus f of x. And this distance is actually only h, because z is x plus h minus x, you're gonna get h. Okay, so this is the distance h, this is the f of x plus h minus f of x. If you take the ratio of this with this h, you get the slope. Of course, you are gonna take the limit as h goes to 0, right? That's why we use the secant line here. We would just let this point Q get closer and closer to the point P, and this is, you can do this by just taking the limit h goes to 0, because point Q is going to be get closer to P if this distance h is getting close to 0, right? Okay, so this is the derivative notion, its definition, it's any x. Okay, so because of this, because of the previous picture, you see that if you let z is equal to x plus h, you get a different expression for this derivative. Look, f of z minus f of x, look at this new notion, new expression. Instead of using f of x plus h minus f of x over h, you can also see it as z approaches to x, f of z minus f of x over z minus x. So this is an alternative formula for the derivative. You can either use this formula or you can use the one with h. Either one would give you the value, okay? For if you use h is going to go to 0. If you use z is going to get closer and closer to x. Let's see the picture. See, this is z is getting closer and closer to x, okay? You can do that only h if h gets very close to 0. Okay. We have a curve which is y is equal to square root of x, and its tangent line at the point 4, 2, which is in red color. The tangent line slope can be found by evaluating this derivative at 4. Okay, so we can do that too. Let me do that for you. In here, our function is square root of x and our point is 4. Here we are using the other alternative formula for you to get used to it. when you drag the plugin z is equal to 4, you're gonna get 0 over 0. Okay, we don't want to do that. Zero over 0 is undefined, so it's not good, okay? We multiply the conjugate of square root of z minus 2. On top, you're gonna see the top part, which is this part. That part is z minus 4, but we have z minus 4 in the denominator as well. They cancel each other, so this thing cancels with this thing in green. And what is left, okay, okay, we got that. We got 1 over z square root of z plus 2. When we want to take the limit, we just plug in z is equal to 4 because there's no undefinedness here. And we got 1 over 4 is the slope at 4. Next, we are going to write the tangent line equation. If you go back to this question, the point is 4 to 2. So x is 4, y is 2. Okay, the thing that you see here, this is the tangent line equation, okay? This thing in red circle is the tangent line equation. Okay, so we did this question as well. This is the example 2 in our book. I want you to see the difference between these two graphs. The first graph is the graph of f, y is equal to f of x. Okay, let me make it a little bit bigger. The second graph is y is equal to f prime. So by looking at the graph of f, you can draw the graph of the derivative function, graph of derivative function. So how would you do? Here, look at the blue graph. This is y is equal to f of x. And at a, we have 0 slope. Look, if you draw a line, it's the horizontal line, so the slope is 0. The function is going down, so it is decreasing. We expect the slope to be negative, but you would see that the slope is negative, which is negative 1. At c, the slope is steeper, so it is negative 1 over 3. Okay, and at D slope is 0 again, it's the horizontal line, and at E it's the, you just approximately calculate that, look at that. Slope at a point can be found as delta y over delta x. We have seen it before, so we just calculate this approximately. We form a triangle here. We just take the opposite over adjacent to find the slope at E. As you will see, if you draw a triangle here, it is 8 over 4, which is going to be close to what? 2. So the slope is positive 2 here. So how are we going to use that to draw the graph of the derivative? So the slope is 0 at A, so the graph of the derivative at A has to be the 0 value of the function, right? Because we are talking about the derivative. Slope is 0, so we put it in. So at B, the slope is negative. So at B, the function f prime takes the value -1. We just plug it in. At C, the slope is -4 over 3. So we, at C, okay, the corresponding x value 5. So we have the little bit less than -1, which is -4 over 3. At D, the slope is 0 again. Look at that, the slope is 0, so f prime function goes through the point D prime here, which is intersecting x-axis. And at E, the slope is 2, so at that particular point, the slope is 2, you see that, right? So you just plug these A prime, B prime, C prime, D prime, E prime, and then you just combine them with a curve like this, and you get this as the approximate graph of f prime. Okay, that's how you would draw the graph of f prime, by using the graph of f and the slopes at some certain points. Okay, that's a good thing to have. Let's see, let me make this a little bit smaller. Okay, here derivative at endpoints of a closed interval. Can we talk about the derivatives at endpoints? Yes, you can, because it's, again, since the derivative is defined in terms of the limits, and we have the one-sided limit notion, so you can just write it in terms of one-sided limit notion. So for example, if you're interested in, let's say the function is defined on the interval a to b, and it's not defined outside of ab. And the blue graph is our graph, y is equal to f of x, okay? And the, let's see, this black graphs are the secant lines, and the red graphs are the tangent lines, all right? Okay, so the red graphs are the tangent lines at point A, and this red line is the tangent line to the curve at the point B. Then, how would you find the derivative? At A, you're going to take the limit as h approaches to 0 from the right, and the same quotient, okay? And if you want to find the derivative from the left at B, you just write the quotient formula, and then you're going to just take the limit as h approaches to 0 from the left, because you're approaching B from the left, all right? Okay, that's how you find the derivatives, one-sided derivatives. Now, let's work on this absolute value of x. I told you absolute value of x is, we will use this over and over. This is an important function. It is very simple so that we can give examples when we are explaining things in calculus, and it's very easy to understand. So I'm going to give you this example to understand, to let you understand that at a point the derivative doesn't exist, because the right derivative and the left derivative, they don't agree. Okay, so let me do that for you. And also you see that there's this sharp corner at 0. Whenever we see a sharp corner for the graphs, then you should say that no, the derivative doesn't exist there. So we are going to show it in particular for this example how it works. But in general, when you see a graph with corners like that, you should say, at that point definitely we don't expect a derivative, okay? So let's do that now. Our function is the absolute value function y is equal to the absolute value of x, and the question is, does it have a derivative at x is equal to 0? So let's see how to answer this, okay? In order to answer this, we look at the one-sided derivatives, and I'm going to give you that right now, okay? We just write the right-hand derivative here. If you go back to it, okay, let's look at the derivative functions. One-sided limits, one-sided derivatives. Okay, so this is this is the definition of the right-hand derivative, and this is the definition of the left-hand derivative, all right? So let's continue from here. So we got that this expression, and this is what is this equal to? Okay. What is this limit? As h approaches to 0 from the right, then the absolute value of h is h. So we got 1 as an answer. Look. So this is going to be, let me see, absolute value of h is going to be, okay, this is going to be just h. Okay, this is equal to h. Alright, so what did we get? Okay. So limit as h goes to 0 from the right, h over h, the limit is 1. Okay, this is the right hand derivative. How about the left hand derivative, okay? So we have seen that the right hand derivative is 1. So what is the left hand derivative? Okay, so we are going to find it similarly. We use the definition of the left hand derivative. Now h takes the negative values, it's approaching from the left of 0. Okay, let me actually draw a line like that, you will see. Okay, let's see. Consider this as the consider this as the 0 here, and this is 0, this is 1, this is 2. Maybe I should make it a little bit bigger. I'm gonna draw this again. So this is like 0 here, this is like -1 here, let's say this is -1, and let's say this is 1 here. So h approaching from h approaching 0 from the left means h is taking values less than 0. H is approaching 0 from the right means h is taking positive values, but these values are very close to 0. Okay, so these are the values here. Okay, so this is our original. Let me make this origin as 0 here. This is our origin 0. Okay. Alright, so then obviously this limit is going to be what? This limit, this absolute value of h is going to be -h now. Okay, this is going to be, okay? So we have -h over h is going to give us -1. Okay, we looked at the right hand derivative, it is 1, and we looked at the left hand derivative and it is -1. If the right hand derivative and the left hand derivative, they don't agree, then the derivative doesn't exist. So we say that since the left-hand derivative and the right-hand derivative, they don't agree, I can make it a little bit bigger for you, and so the derivative doesn't exist. Alright, so let's see. Yeah, I can highlight this as well if I want. Okay, highlighting is not as good, so I'm gonna erase that. Okay, that's the point. Alright, so we just say we are done. Okay, that's the end of this question. Similarly, one can show that y is equal to square root of x is not differentiable at x is equal to 0, because if you look at the right hand limit, the limit is not going to exist. Okay, we have a vertical tangent line here. You can only draw a vertical tangent line here. Okay, so it doesn't exist. So there are three types of situations here. We may where the derivative does not exist. So we may have a corner. Look at this blue graph, and then there's this corner right at P. There's a corner, and if you have a corner, in this case we have the one-sided derivatives differ here. Because of that, the derivative at P doesn't exist. So if you have a corner in the graph, forget about the derivative at that point. A cusp is where the slope of PQ approaches infinity from one side and negative infinity from the other side. Okay, so we have a cusp here. So if you write down the right hand derivative and the left hand derivative, then you're going to see that these derivatives are on one side it's infinite, on the other side it's negative infinite. Then you have a cusp at P, so the derivative doesn't exist. And we have a vertical tangent line situation like in square root of x. So how does it happen? So we are going to look at the right hand derivative and the left hand derivative. In this case, the right hand derivative and left hand derivative, they both approaches to the same infinity, plus infinity, or they may both approach to negative infinity. Okay, so in that case we have the vertical tangent line there. Okay, all right, so we have a fourth situation where discontinuity. Let's say you have a function like the blue one here. There's a jump here, so that means this function is not continuous. If you have a function that's not continuous at a point, then forget about the derivative. Derivative doesn't exist there. Okay, all right, so for example here, this is another example. This blue color graph, and at P there's a big jump. Okay, so there's no way you have the slope there. And we have the wild oscillation. We have seen it when we worked on sine 1 over x or cosine 1 over x, right? And you have such a situation. We have infinitely many ups and downs as x approaches to 0 to the right and to the left. And here we don't have even, we don't have the derivative in here because you wouldn't be able to get the one-sided derivatives. Look, there are tons of derivatives here. These red colors, you're going to see the tangent lines. And there are infinitely many of such. So how come you're going to get one single derivative value at 0, right? So, okay. And this theorem 1 is important. Differentiability is always stronger than continuity. So if a function is differentiable, it is automatically continuous. So this theorem says, actually, if f has a derivative at c, at x is equal to c, then f has to be continuous at c. So this is a nice theorem because this is making your job easier by just, if you can first determine a function is differentiable, you don't have to worry about the continuity at that point. Okay, that's the end of today's talk. Thanks.